All right, section 2.5, part 2. We're going to be graphing special functions right now. So talk about, so this is just sort of a hodgepodge of different interesting functions. We talked about piecewise defined functions at the beginning of 2.5. Today we're going to talk about step functions and absolute value functions. Okay, so the first type of function, a step function, is best or most frequently analyzed using the greatest integer function. Okay, and what this does is it graphs the greatest integer that's less than or equal to x, or in other words, whatever you put into the, whatever you put into the function. So you can see the graph of it here, but I think it'd be worthwhile taking and just looking at a few values. F of x equals these like double braces is how you type it in, but really if you just use braces, we'll know what you're talking about. So how does this function work? Well, let's take a look. What if we want f of 0? Okay, f of 0 would be greatest integer of 0. What is the greatest integer in the number 0? In other words, that is less than or equal to 0. Well, it's 0. 0 is an integer. You can see that on the graph right here. It's plotted right there. Okay, so that would be 0. All right, well, that's not a very interesting one. Let's try f of 1.2. Okay, what is the greatest integer that is less than or equal to 1.2? Well, that would be 1. So the greatest integer function value of 1.2 would be 1. And you can see that on the graph. If you go over to 1.2, so just past 1, you're still plotting 1. Okay. In fact, this graph will be 1 all the way up until you get to 2. So in other words, if you plugged in 1.9, it'd still be 1. But once you hit 2, it jumps. And then it's 2 until it hits 3, and then it jumps again, and so on. So you can think of this as like lopping off the decimal or truncating the decimal. So like if you put in f of 7.9, the value would be of the greatest integer of 7.9 would equal 7. Okay? That's how the greatest integer function works. Now, any of these functions can be, you can do things mathematically to them, right? So you can add numbers to the function, you can multiply the function by a number, you can divide it by a number, whatever. So let's take a look at what happens when we take the greatest integer function and subtract 6. All right, I'm also going to show you how to graph this in your calculator as well. So we want to graph the function and find the domain. Okay, now the one problem that I have with the TI-83 pluses, 84s, or whatever, I think the colors, the newer calculators are a little bit better with this. But I'll show you what my problem is here in a second. If I hit math, and then I go over to number, and then down to int, that's how I'm going to graph the greatest integer function. Okay, I'm going to put an x in there. So int of x, greatest integer function of x. So hit graph. This is the problem. It connects these line segments. Okay, so this is what the graph actually looks like. But your calculator is not smart enough to not draw in these vertical lines that connect the pieces here. Okay, so it can give you a misconception of what the graph looks like. You should not connect these lines, all right? So I really like the way that Desmos does it, which is the right way. And so to show you how to do this in Desmos, what you're going to do is take and pull up the functions. Whoops. So right here, you're going to pull up functions. Okay, and you're going to go over to miscellaneous, and you want the floor function. Okay, the floor function is the same. It's the same as the greatest integer function. So if you hit floor of x, you will get a graph of the function. Okay, and so you can see the step-like behavior there. Now, what I want though is I want the floor function. I want the greatest integer function minus 6. Okay, so I'm going to put in floor. In fact, actually, let's just make a copy of that. Okay, so minus 6, and what this will do is it shifts the step function down. In fact, it shifts it down 6 units, so it's a little bit tough to see here. I don't know if I can show you on the, yeah, I could be able to. But anyway, you can see that it's down 6 units from where it was before. So anyway, so let's turn this one off. That's the graph that we're analyzing. And we can do one of two things to get some points here. We can just look at the graph, or we can use the table. But the graph is pretty easy to look at. So you can see that this graph starts at, 6, I guess. So go over 6, put an closed dot, open dot, and then it steps up 1 every time. And I gave you guys a bad graph, so it's going to be very hard for you to graph this well because I gave you the scales too small, but you get the idea. It's going to keep going down like that kind of behavior. Okay. So what is the domain of this graph? The domain is all the x values that the graph covers. the graph is going to cover all the x values here, right? No matter what number you plug in for x, there will be a y value that gets plotted. Okay, for every input, there's an output. So we'd say the domain is all real numbers here. So the domain is all real numbers. We're not going to worry about the range. The range is all integers. We're not going to worry about that. Okay, so this takes the greatest integer function, moves it down. Okay, let's talk about a different type of function now. Let's talk about absolute value functions. Okay, so here is f of x equals the absolute value of x. Be careful here. Absolute value is straight lines, right? So this is the absolute value. Okay, greatest integer function uses these braces here. Okay, all right, so here's a graph of f of x equals the absolute value of x, and all this does is whatever you plug into the function, it makes it positive. So if it's a positive 2, it plots it at 2. If it's a negative 2, plots it at positive 2. That's what absolute value does. What is the domain of this function? In other words, what are the x values covered by the graph? What inputs also have outputs? These all mean the same thing. This is all real numbers. This graph goes forever to the left, forever to the right. It covers all of the values on the x-axis. Okay, so this has a domain of all real numbers. The range, that's all the y values that the graph covers. So if I asked you, is negative 2 in the range, you would say, no, it's not in the range, because you'd go to negative 2 and be like, there's no graph down there. So where do the y values pick up? Well, they start right here at 0. And then they keep going. Okay, so it's all numbers that are greater than or equal to 0. So we can write that as y greater than or equal to 0, because we're talking about y values. We're including 0 because this point is on the graph, and it's everything above it. Okay. So we want to. So that's the absolute value function. That's called the parent function, by the way. A parent function is the simplest version of the function. So this is the parent absolute value function. But like any function, we can do stuff to it, and we can move it around if we want to. So let's graph absolute value of 2x minus 4. Find the domain and range. So I'm going to go to Desmos. Well, actually, no. I'll show you in Desmos. You just type in ABS. Okay. So here we're going to go math. And then we're going to go down over to number, and ABS is right at the top. So then we'll put in 2x, close parenthesis, and then minus 4. That's what we're trying to graph here. So there is the graph. And again, to get a plot of that, the easiest thing is to go to your table and plot some points. So I've got the point negative 2, 0 is on there. I have the point, let's see, negative 1, negative 2. The point 2, 0. Whoops, I think I missed one, or 2. Let's see, 0, negative 4. And here, and you get an idea. This graph looks like this, okay? So then the domain of this is going to be, again, all real numbers, because this graph goes forever to the left and to the right. So it's all real numbers. The range is all the y values that the graph covers. It starts at negative 4, and goes up forever. So the range is y greater than or equal to negative 4. Right? Move on to number 5. Graph the absolute value of x minus 2 and find the domain and range. Okay, so absolute value of x minus 2. Why don't I just show you that one on this calculator here, just so you've got both that you can look at. Absolute value. You can just hit the absolute value bar is 2 there if you want. Absolute value of x minus 2. What that does is moves the absolute value graph to the right. And again, you can see some points here. If you want to turn that into a table, hit the gear and hit the table, and you can see there's some points that we can plot. Okay, so we do that real quick. 0, 2, 1, 1, 2, 0, and same going the other way. This has line symmetry, by the way. Remember from an earlier section, talking about line symmetry, it's symmetric about the line x equals 2. Okay. Domain, all real numbers. Range is y greater than or equal to 0. Starts at 0 and goes up forever. Okay. Last one, you should try this on your own. Pause the video, give it a try, and then I am going to, I'll do it real quick here. You should check your answer. I made a bad graph. All right, but anyway, so that's the graph of it. The domain on this, again, goes forever to the left and to the right, covers all of the x values, and then the range This one, we got to be a little bit careful. It's pointed down this time, so it starts at 1 and then goes down. So the range here would be y less than or equal to 1. Right? And that's it for section 5, graphing special functions. We've got 2 new ones there, and that pretty much wraps it up. A lot of the section is just taking the absolute value or the greatest integer and moving those functions around and seeing what happens. Right?